These are the notes for Tuesday. My pen right here. For Tuesday, the 5th. And these are on 4.3a. And open your packet to the page that looks like this, but before we go fill this in, I'm going to give a little pre-talk here. So just watch and then we'll start filling in the notes. So we've been working with approximating the area under a curve on a given interval. So I'm going to call that interval from A to B, and I'm going to go draw this area under the curve, and I'm not going to shade it, but pretend it's shaded. And my goal is to approximate what this area is. Notice I can't find it exactly yet because this shape created by the area under the curve and above the x-axis is irregular. It's not a perfect rectangle, triangle, trapezoid, or something like that. So we've been given two ways to approximate that area: to chop it into rectangles that either hit on the left, and we call that a left rectangular approximation method. Rectangles that hit on the right, we call that a right rectangular approximation. Rectangles that hit the curve in the middle. And the trapezoidal rule, which we chopped it into trapezoids. But we chopped it into a finite number of them, and that gave us an approximation, because when we go up and say hit like right here on the left, or maybe we go up and hit the curve on the right, we don't quite get all of that area, or sometimes we get, like here, if I hit on the right, extra area. So those are all approximations for the area under the curve. And our next task is, how do we get that approximation to be exact? And the theory behind it is, if I could chop this into an infinite amount of rectangles that are each have a base or a delta x that approaches 0, so they're so thin you can't even see it, and I do an infinite amount of them, watch me start drawing them as best I can. Keep in mind these are still way too big because the base of the rectangle should be so close to 0, like 0.0000000 to I croak over and die and call it 1. And if I make an infinite amount of them that are that thin, and if I were to continue making those rectangles all the way over to B, I would get the exact area under the curve. Well, what am I doing when I'm doing that? First of all, I'm trying to make an infinite amount of rectangles. So I'm going to be taking a limit as the number of rectangles approaches infinity. And then what I'm going to do is take the area of all these super thin rectangles, of which I'm making so many of them, and I'm going to take the area and add them all up. Well, in math, that's a summation symbol. And I'm going to be adding up an infinite amount of them. So I say that's where I will go from, and you can either use 0 or 1, to the number that I have, which is going to approach infinity. So this whole language right here says I'm going to add up an infinite amount of what? Of the area of every rectangle. Well, a rectangle's area is base times height. The base of every rectangle that I make, and now I'll blow one up. Actually, I have one blown up here. We've been calling that delta x, which when it gets infinitely small, we change that to dx. But basically, delta x and dx just mean a change along the x-axis. And so we're going to have the bases of all our rectangles be dx. The height of all our rectangles, remember this is the function f of x. And maybe right here I'm at point, doesn't really matter, x sub 5, and like the 5th rectangle. Then the height is the y value there, or f of there. So we call this f of x sub I. Now this notation is very cumbersome. What we do is we replace this whole part of it with a symbol, and that symbol is one you've already seen, an integration symbol. It kind of looks like an S, which kind of helps for sum. So we say we're going to add up all those rectangles, which we call f of x dx. Again, these are just bases times heights, and we're going to sum them up on an interval. So this notation right here is new, but what this just means is, notation-wise, you are going to add up an infinite amount of rectangles, which will yield the exact area under the curve. Exact area under the curve. So the next thing we're going to do is go to the notes, and we'll kind of tie all this stuff in. So the area under a curve on a given interval from A to B is now going to be denoted with this symbol. We're going to put limits on our integral symbol, f of x dx. It's kind of like when we first started talking about derivatives, we said dy dx is the derivative, and then we said really what that stands for is the slope of the tangent line. Well, this symbol right now is an integral, and a and b represent what we call the limits of integration. But really what that means is, yeah, it's a definite integral, but what it means is find the area under the curve. Like this means find the slope of the tangent line. So A and B tell you where on the curve under which to find the area, and f of x is the curve under which we find the area. And we'll do a couple in a little bit, and if you're confused, you won't be. Everyone thought this lesson was really easy. So I have put some of these on the next page, so you don't need to open up your book, but I kind of want to talk about this next paragraph here. It doesn't have any math in it, but the concept behind it is huge. So just as the derivative was defined as the slope of the tangent line, anywhere on the curve. So when we had a curve and we did the derivative right here, we were actually finding the slope of that line. Well, the integral, technically the definite integral, is defined as the area under the curve and above the x-axis. So recall that the derivative in a real-life context, when we did dy dx, but we started doing these with real-world problems, well, what's constantly changing in the real world is time. So we usually had some function, I'll call it w, changing over time. You can even think of velocity where we did change in position over change in time. Well, that fraction bar really means per in the real world. Like if I were to do miles over hours. That's really a rate of change in miles per hour. So a derivative in real life context is a rate of change. Like feet per second, miles per gallon, gallons per minute, they're all rates of change. Well, integration is the inverse of differentiation, meaning it undoes it. So whereas each derivative adds the word per, it does. Think of when we did our position, velocity, acceleration. This was in feet. This was feet per second. This was feet per second squared. Every time we took a derivative, we added another rate of change, or technically another word per. Well, integration undoes that. So it removes the word per, and it gives us, for example, if we were doing feet per second, velocity, and we integrated it, we'd go just back to feet. It makes sense graphically with the area model. So suppose we were charting velocity over time. And suppose we were doing time in hours and velocity in miles per hour. And we charted different velocities at a different time. Maybe the brakes were hit right before an accident, so the velocity started going down. And we look at the curve created. When I look at the area under the curve, let's make a rectangle here. Let's talk about just the area of this green stuff. It is some measure of time, which is in hours. It's some hour increment times miles per hour. And you'll notice hours times miles per hour yields miles. So that per goes away, and this green area represents how many miles I traveled over that time interval. And we'll be working with that in depth later. For now, you need to get the concept down that when we are integrating, we're finding the area under the curve. So when you see an integral and you see from 5 to 7 x squared dx, your answer will be a number, and that number will represent the area under this parabola between these two values on the x-axis. And Conversely, when you find the area under the curve, you have technically evaluated a definite integral. So first thing we're going to do is just practice setting some up so you get used to the language. These are some of the evens from the books. You might see a repeat of some of these in your homework. So it says to set up a definite integral, which means I need an integral, but I also need to provide limits of integration. Those are given by the span along the x-axis. This one's going to go from 0 to 2. The function, the f of x that I'm integrating, is 6 minus 3x. That's the line under which I'm finding the area. And then the dx also needs to be there. So this is the definite integral that represents the area under this curve. Let's go do the next one. Again, I am integrating, finding the area under the curve from 0 to 2. My curve on this one is the parabola f of x equals x squared dx. And the third one, I am integrating, in this case, from -1 to 1, the area under the curve, which is represented by 4 over x squared plus 2 dx. Now this one I could have done differently, and it will be to your benefit later to do when we start doing these analytically or with some algebra. Right now we're just looking at the geometry of it. But when we start doing the algebra, the easiest number to work with when you're working with algebra is 0. So I could actually maximize my use of 0 with this one because of the symmetry. I could just integrate or find the area from 0 to 1, which would yield this part of it, and then double it. Either one of these is sufficient. This one will be better later, so kind of know that. Now, of these three, there's one of them I can find the area of exactly right now. I can't with this one right here because I have no formula for this shape. Eventually, I'm going to be able to get it, but for today, I can't get that one. Same here. This has got curvature to it, so I have no idea what the formula is for the area of something shaped like that because there actually isn't one. Doesn't mean I can't do it. It means there's not a formula for it. But this makes a triangle. So this one's area I can actually get. Its area is 1/2 of its base length times its height. The base length was 2. The height is 6. So it's 1/2 of 2 times 6, or 6. So this one right now, I know the exact area, or I know the value exactly of the definite integral. It is not an approximation. That area, that stuff is 6. I can't figure this one out yet. Later in the chapter I can't figure that one out yet, but later in the chapter I can. In this section we're going to be concerned only with the ones that make geometric figures that you know a formula for. So they will either make rectangles, which have an area of base times height, triangles, which are 1/2 of the base times height. Circles they won't make because a circle's not a function. It fails the vertical line test, but it might make 1/2 of a circle or 1/4 of a circle. So you might have a scalar multiple out front here of either 1/2 or 1/4, and you might be integrating under part of a circle. And trapezoids, which have formula of 1/2 the height times the sum of the bases, which we talked about in the last section. So before we start going and doing some of these, another thing to know is that although the definite integral yields a number that represents the area between the curve and the x-axis, we got to be a little careful with that because when the curve falls under the x-axis, so let's go put 1/2 of a circle, oops, I'm going to make that radius exactly 2 here. So let's say we had a circle of radius 2 that falls, I did it again, radius 2 that falls under the x-axis. This is 1/2 of a circle, and we know it'd be 1/2 of pi r squared, which would yield 2 pi. That is the area of this stuff. But when I do the integral from -2 to 2 of that function, right, let's call that f of x right here, what I'd actually get is, because it's below the x-axis, the y values, or the f-ofs down here, are negative. The change along the x-axis is still positive because I'm going from -2 to 2, so delta x is moving in the positive direction. So what happens when I evaluate the definite integral from -2 to 2 is I actually get a -2 pi. So to refine our definition of a definite integral, it's the signed area under the curve. So if we follow up here, yeah, this one does have an area of 2 pi, but the one down here we say has an integral value of -2 pi. So we are going to sketch the regions. So let's go do that. Make a little graph. My function on this one is f of x equals 4. So from Algebra 1, we'll call that y equals 4 is really what I'm graphing. We should all know that that makes a horizontal line through 4. It's called a constant function. I am being asked to evaluate the definite integral from 1 on the x-axis to 3 on the x-axis. So I put down those limits. I drop my limiting lines down. I shade in the region, and it makes a nice geometric shape that I know the exact area of. It's a rectangle that's 2 by 4. So this would just be 2 times 4, which is 8. It's not an approximation. It's exactly 8. But again, if I had my f of x dip down in here instead of being constant, then I can only, for now, approximate what that area is. But when it makes one of our nice geometric figures, we can do it exactly. So let's go to part B here. Again, I'm going to graph my f of x, or my y equals x plus 2. That's a line that goes through 0, 2. It has a slope of 1, so it goes up 1, over 1, up 1, over 1. The line heads about like that. I'm going to integrate from 0 to 3. So I'm going to drop down my limits of integration. I'm going to shade it in. I'm going to realize that it makes a trapezoid. And for a trapezoid, I need to evaluate 1/2 of its height times the sum of its bases. The parallel ones are the bases. The height is the distance between the bases. So I would do 1/2 of 3, 1/2 the height, times the base 1 right here, which is up at 2. And the next base, which you might say, I can't see that on the graph. You don't really need to, because again, you can just plug it in to figure out the y value there. So it would be up at 5. So this one would give me 7 times 3 is 21 halves as the exact area under the curve. There is no need to chop it into rectangles and approximate it, because I can find it exactly, because it makes a geometric figure. So the next one, and the last one of these, again, we'll call that f of x, aka y. And you might not recognize the graph of that, but watch it evolve as I rewrite it as y is equal to the square root of 4 minus x squared. I'm going to square both sides. I'm going to add x squared over. And this should be really familiar to you from your previous math classes. This is the equation for the area of for the graph of a circle. It would be centered at 0, 0. This is r squared, so it would have a radius of 2. Because this was a positive y, that means I am going to be having the portion of the circle that falls above the x-axis. So I have a circle with radius 2, and I'm on the positive part. Again, the reason I know it's the positive half is because if I were to reverse this and solve for y, when I undo this square, I'd have plus or minus the square root, which would be the whole circle. But in the integrand here, I just have the positive. So I know I'm dealing with the top half of the circle. And that's what I need to find the area of. I need to integrate it from -2 to 2. What that'll do is make all these little rectangular things, and when I'm done, I'll have the area of the whole thing. But when it's all done, it's really just half of pi r squared, and my radius is 2. So it's a half of pi times 4, or 2 pi. And it's positive because it's above the x-axis. But had I been integrating the part below the x-axis. The value of the integral would become negative. So you got to be a little careful. Integration gives us the signed area. So now we'll go take a couple more. And in class, we didn't do this one because everybody started thinking this stuff was really easy. So we skipped a couple and we just did a few. So again, I'm going to begin as normal. I'm going to graph my function. Eventually, we'll stop graphing. And eventually, we're going to add a whole bunch of funky shapes to this. But for today, your graph will yield some geometric figure that you can find the area of. So I'm under the curve, f of x equals 4. I'm going from some unknown a to the right and the same amount to the left. I'm going to drop my limits. I'm going to notice that I'm finding the area of this red rectangle. Its base times height. Its base is a this way and a that way, so twice a. And its height is 4. So the answer to this one, an expression for the area, would be 8a. And lastly, we don't need to do number 5 either. I just did one like that with a circle. So lastly, this one might not look too familiar to you, but I'm going to rewrite it in a form that's a little bit more user-friendly so you can kind of think it through. First thing I need to do is graph this function. Well, we've got to think it through. It's the absolute value function, which, I'm using this off to the side, looks like this. But the negative in front flips it over so it looks like this. And the plus a moves it up, a on the x-axis, because it's adding, remember this is y equals, when you do plus a, it's going to move it up the y-axis. So my graph of this one is going to be an upside down upside down v, because the negative flips it over, but it's going to be moved up a on the x-axis, and it's going to hit at a, negative a, and I'm to find the area of that triangle. And the area of a triangle is a half of its base. This one's base length right here is twice a, or 2 a's. It's an a to the right and an a to the left. Its height is a. So I do 1/2 base times height, which yields a squared. And that's it. The assignment was 13 through 31 all on page 278, and it took kids about 15 minutes to complete that. It was pretty quick. Have a good one.